in. What will this give you? This will basically give you a bunch of numbers. If you have 8 gigabytes, then it's roughly, and also literally, 8 gigabytes. So 8 means 8, of course. Giga means a billion. In German it's Milliarde, don't get confused. And times 1 byte. And the byte is the important thing. If you don't know what a byte is, so just raise your hand if you don't know what a byte is. That's good. Just counter check who knows what a byte is. Okay, and who's not paying attention? Okay. Again, you have about 8 billion bytes going on here in memory. And all of these bytes is 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. Embarrassing if I don't get this number right. Okay, 8 bits. And a bit is either 0 or 1. And of course, your computer doesn't know that a byte can also represent a number. Your computer only knows zeros and ones. For example, having all bits set to 0 can mean the number 0. Having a 1 here gives you the number 1. 0, 0. This is basically like 255. This is basically your normal base 2 binary system. But this is only a convention made by people to make it easier to understand what's happening inside of the computer. Again, the computer will only see zeros and ones. If you say to the computer, well, add 2 numbers, it will happily do so, but it won't understand them as numbers. It will just look at these sequences of bits, and when you tell it to add these 2 sequences, it will do some kind of bit operations on them, not knowing that these are actually numbers to us. So this part here is actually inscribed also. This part is inscribed to these bit patterns by us, as the programmers. This is only a convention. For example, in C there's not only 0, 1, 2, there's not only numbers. You might have already heard about true and false, which is also the same as yes and no. And often 0 means false in the system and 1 means true, or yes. So you can assign multiple meanings to bit patterns, and it doesn't have to be 1 byte. It could be 1 bit, or it could be multiple bytes, it could be the entire memory. You're the one who defines things. You're the one who's going to keep the order of these things straight. In the end, what's going to matter is that what you define these numbers to be, that this is convenient, that it matches what other people are defining. So if you define 0 as true and 1 as false, you can do that in your code. But other people will punch you for this, because they're not going to understand things. Again, coding in C means you're writing in a language that other people are going to read. Therefore, stick to the conventions mostly. You can invent your own if you want to, but then make it clear that you stick to other conventions. Like, it's really important that everything we do in our languages, even numbers, is all nothing to the computer. The computer only cares about zeros and ones. And whenever you write code, pay attention that all of these numbers mean exactly what you intend them to mean. So in C, for example, you have pointers, you have numbers, integers, you have characters, you have the null pointer, you have the null character, you have 0 as a number, and you can convert them happily back and forth, because to the computer they're all numbers. When you have, for example, I think most of you know the null pointer. Quick check, who knows the null pointer? Awesome. To the system, the null pointer is actually a bunch of zeros. Actually, it's mostly 64 if you have a 64-bit computer, so it's 64 zeros technically. You could, of course, treat this as an int, an integer, which is a number, and get out the number 0 out of it. So I've seen many people do, well, check if the pointer is equal or not equal to 0 then do something. And this is a pretty dangerous mistake to make, because P is a pointer, not a number. To the computer it's just bits, but in the end what happens when you do this is you're comparing a pointer, which is referencing some data. I'm also going to explain that at some other point. You compare this against a number, and a number is not a pointer. A number is a number, and a pointer is a pointer. This is important. If you do this, you're basically comparing two things that are not similar, or that are similar in its representation, but not in its meaning. And once you do some of these mistakes, you might even confuse something like a char pointer and a char double pointer. And once you're confused about these, it's really important to get back to step 0. Because once you forget about the difference between those, once you get confused which one you should actually put inside of your code, then you're basically doing the same mistake as this one. You take one type, which is the char double pointer, and use it as a char single pointer, or the other way around. So in the end, it's easy to confuse things in C, because C is just a thin layer of abstraction on top of these numbers. This is basically my point. And if you forget that everything's just numbers to your computer, then basically you're already lost from the point number 0. Does this make sense to you? Okay. Nice. So actually what you can do is you can maybe gather in groups at some point and just look at some mistakes or misunderstandings that you often have. Just find friendly people and ask them, what mistakes did you make? And what mistakes have you noticed? And what are you paying attention at? And to what are you trying to do in order to avoid these mistakes? Just talk to people, ask them what their strategy is to avoid these things, and just try to adapt and learn new things from this. This is basically what I can tell you about these types of errors. They occur. Make a list maybe. Whenever you see, oh, this wasn't so good after all, make a list. Like, really do this. Keep a list. Always get back to that list. Read it over and over again. And whenever you see yourself writing something like this, that's at some point in your list, stop yourself, turn off the computer, don't shut it down, turn it off at some point, log out, whatever, and give yourself some time, think about it, and then write it considering the mistake and try to fix things. It's a slow process. It might hurt you. You might not get all of these mistakes, but in the end, if you start keeping a list right from the beginning, after half a year, you have a list that's so big that basically most errors are covered. And once you have that, whenever you have a crash or segmentation fault or whatever, you can get back to that list and find the most recent change you made and look at this, and you'll most likely see what you did wrong there. So debugging and finding errors becomes a lot more easy and efficient if you make a list of what went wrong. Also, what's happening quite often is people not knowing what to write. We had that a few times in the beginning, that people didn't know, well, I've thought about the problem, they say, but I don't know what should I put there. How do I actually write code? How do I put the pieces together? Is there an if statement that should be inserted here, or while statement? Should I write a function for this? This is something you cannot simply answer by this. What the CPU does is, again, it only looks at numbers. It won't give you an answer to this. The answer you're going to get is by looking at other people's code and learning from them. And the more you look at other people's code, can I clear this off? Okay. The more you look at other people's code, the more you notice patterns. And patterns are the most important thing about learning how to code C when it comes to the actual language. Because I've seen people writing code line by line before, like they write one line, then they write another line, then they insert at some point another line, but this is not how you write C code. You write C code in patterns, which are basically blocks of lines. So, so you might notice that I'm switching between topics here, because everything is interlinked in some sense. In the beginning, everything is basically connected. So, yeah, one mistake might easily lead to another one. And what I've often seen people do is they have line 1, line 2, line 3, and they write and read code line by line. You have int main, then you have this brace, then you have maybe int x, then you have an empty line, then you have a while statement, and so on. You get the idea. Many people, when they first see code as a bunch of lines. And this is not how experienced programmers see code, or code C. What they often do is they separate, like for example, if you have int x, int y, they take blocks of code and treat them as one unit. For example, this, as you can see here, you have two lines that look basically the same. They do the same thing. One of them introduces a variable called x, which gives you an integer, or which is an integer, and the other one gives you or creates a variable called y, which is also an integer. This is basically the variable declaration pattern. What you'll also see is something like while, then you have some kind of block here. It's like the fill in the gaps text. So in German it's Lückentext, or in English like fill in the gaps. So you have some kind of text that's already given to you, and there's some blanks in between. And these blanks is basically what you have to fill. So when you're at, well, that's a curly black brace here. Not getting better, but okay. If you don't know what to write, it's often the case that your cursor blinks here, and you don't know what to insert. And you have to think of a line that you want to add. No, it's more often the case that you're looking for some kind of fill in the gaps block. You might not know all of these, or maybe not know any of these from the beginning, but if you pay attention to the blocks right from the start, make a list of blocks that you encounter, things are going to get easier pretty quickly. If you're stuck at lines, it's going to be hard to learn how to code. If you notice that some things are just connected, and there's just some blanks in between, you don't write line by line, you write first the block and then you fill it in. And then it becomes a lot easier to think about code, because you don't look at it line by line, you don't look at it like int x, and then you don't know what x fits in a context. Here you know this is a while loop. And maybe if you have an I equals 0, of course you need an int I for that, but let's assume we have one. If you have a block like this, and then in here there's something like I less than some kind of number. And then in the end, not inside of this block, but in the end, there is I plus plus, or I equals 1, I plus 1, or whatever. This is, for example, an iteration pattern, also or a counting loop. And what this will do is, it will just call or execute this pattern, whatever it is. You can fill anything in that you want. It will execute this 100 times. As long as you don't use I in here, this one will just get run 100 times, one after the other. And inside of here, you don't even need to care about this pattern anymore that's outside of it. You can now just assume, okay, I'm now running 100 times this block. And this takes away some complexity, because if you look at it line by line, you're going to see a long function with whiles and braces and all the other stuff. But if you pay attention to these blocks, you only have to look at this block, and you know that this block is going to be executed 100 times. Because this is what this is actually for. If you have maybe n in here, and there's a variable called int n, and at some point you say n equals whatever, input, and input gives you a number from whatever reason, like, then this is going to be executed the result times, n times, and whatever n is, you decide from input. But regardless, this block will be executed 100 times, or n times, whatever you want. And once you start looking at code like this, so blocks that you can take out and replace, you don't have to have the entire function in your head at once. You only have to look at one simple thing. And the context, I mean, if something breaks, if it doesn't get executed 100 times, but 99 times, the error is somewhere in here, it's not in here. If this code gets executed 100 times, but 100 times does the wrong result printing on the screen, then the error is probably in here. And if you use some kind of variable in here that was loaded right above, then the error might be in here or in the variable that it refers to, whatever variable it has, for example, x. Then it might be at some point we're setting x. Or maybe you forget to set x at all, which is also an error that happens quite often. But in the end, look at code like this, in blocks, in pieces, and there are many of possible pieces. So this one is only one version. There's also the string iteration pattern, which is like you don't count, or basically you do something similar to counting, but what you actually do is you have a piece of text like hello, and let's say you wanted to execute this block of code for every character. Like execute this code for character H, this code for character E, this code for character L, and so on. So you can repeat things, and so you can say, okay, I have another pattern going on here, which looks like this. For example, we can say char pointer s equals hello, which basically creates a new string called hello. And you can now say, okay, while the character that s is pointing to, this is complicated stuff. Pointers are something that I can do a whole lecture about, which is what I'm going to do probably. While s is not equal to \0. Are people who have used this? Like, do you know what this means? If you don't, please raise your hand now. Don't be afraid, but it's important. Okay. So, is it more about the pointer? Is it about the star? Or what is it about?
The pointer.
The pointer, okay. What this essentially does is a string in memory, like when we look at the bytes again. Again, questions are good, by the way, so it's a good chance to get into the detail and make sure that we understand everything. When you declare a string like this, somewhere in your computer memory, so you have a lot of bytes here, a lot of bytes there, probably 8 billion, somewhere in here you have H, E, L, L, O. And in the end, there's a special character called \0. In the end, all characters, again, the computer only understands ones and zeros. Nothing more, nothing less, ones and zeros. So what the computer will do with this is it will put some kind of bit patterns in here. 1, 0, 1, 1, 1, 0, whatever. You don't know exactly what you could figure out, but let's say we don't know what these bits are. We just say to the C language, to the C compiler, not to the computer, but in this case to the C language, put some bit patterns in here that represent the text hello, according to the C language's normal standard. So there's other ways, for example, if you put zeros and ones here, and you put different zeros and ones, it might still mean hello in other contexts. So it all depends on you, what kind of number pattern. I think the number 42, which is the bit pattern, I don't know. I don't really know the bit pattern, but number 42, which is also a bit pattern, often corresponds to the character style, like the asterisk that you also use in multiplication and stuff. Or the letter A, I think it's 63 or 64, I don't know. I think 48 might be 48. I'm not sure about this, but 48 is the character 0.
Yes.
So this is called the ASCII code. ASCII. There are also different codes where the number 0 actually means the letter 0 or letter A. There are different sets, but we work often with ASCII. Again, it's important that you don't mix things up, but so when I tell the computer or the C language to put some kind of bit pattern in here to represent this, in the end what happens is we get some bytes in the memory. We don't know where they are exactly, but this variable knows. So the C language will provide a variable which works pretty much like an integer. And this variable contains the number of the byte where everything starts. So since this is 8 billion bytes, it's probably a number between 0 and 8 billion. So we might say, okay, this is byte number 128,042. So this might be a number, again a bit pattern, that's stored in this variable. And what this basically means, if this star means this is a variable that stores a bit pattern that has some memory location associated with it. Like when there's a star, so a char star or an int star, the first thing doesn't really matter. What's only important is the last star. And this last star basically tells you this variable is containing, again, a bit pattern, some kind of zeros and ones, that represent the number where in your computer memory your data starts. Again, it's a bit pattern. It could also point to something entirely different, maybe a phone number or some kind of IP address, computer ID, whatever you want. Fractional number, I don't know. You decide what your bit patterns mean. A pointer basically tells you, not the chart, but the pointer basically tells you that S is a number that contains a memory location. And what this does is, the star in front of it basically tells you that what this is going to end up as is the character or the data point at this memory location. So when I put a star in front of S, it's not going to give me the number that's stored inside of S. Basically, it's not going to give me the 128,000 and so on. It's going to look into this memory address. So you could actually type in the address of whatever number you want to have here, or you could just type S, and it will go and fetch the contents in here. And since it also has to know how many bits or how long this sequence is, this is why we write char. Char means a byte, which is 8 bits. And since every character is 8 bits in this encoding, ASCII, what this will do is it will go to S, so here, and it will fetch me whatever is in here. And in order to know how long the sequence is that it's going to fetch, we write char, like this is what the variable contains, so it contains chars. So it's going to fetch me 8 bits from this memory location, which is the current character, as we would say. And this \0 is basically the character 0. So there's a special character called the string termination character, which is often actually the bit pattern 0, 0, 0, 0, 0, 0, 0, 0. This is actually the most common representation of \0, which is also not this 0. This 0 is often 48, so it's pretty confusing. So \0 is something different from 0. And \0, just like \n is the new line, \0 is the magical string terminator. And whenever you see a string pointer, a char pointer, pointing to \0, this is basically the end of the string. So again, when you say to the system, put hello in memory, what it will do is it will put hello followed by the string terminator so that you know where your string stops, because you don't have a length. And since everything can follow, and everything can be converted, like the sequence can be converted to characters, if you forget this and have some kind of, like if you have no terminator here and no length in your head, how long this is, it might go on with completely weird stuff. And you might have already seen this if you forgot the null terminator or check against it. You might have seen that if you print this string, you might end up with some garbled output and maybe a segmentation fault even. So when you get a segmentation fault, this means that you're accessing some memory that doesn't belong to you. And this is actually what's happening. So in order to know where the end of a string is, always when you put something in double quotes, there's a hidden \0 character in the end. So when you want to, let's get back to the patterns. This one was a counting pattern, doing this 100 times or n times. What this pattern is going to do is it will basically execute this block for every character inside of the string. And so it will run this block for H, for E, for L, for O, and not for the \0 because it's not part of the string. It's part of the data sequence here, but it's not actually part of the text that you inserted. So what this will do is, as long as the current character, so the character that we are pointing to, as long as this isn't this special \0 character, we have a character that's valid that we're pointing to, so we can run this block. And in the end, what we do is S++, which basically means S is equal to S plus 1, which means out of the 42, put a 43 here, and this basically shifts this pointer to here. Then we just continue And as you can see here, while again we get the contents of S, which is the character E. Again, it's the character E, so it's in single quotes. We compare this against the magical \0 character. It's not equal, so we do the while loop again. So this block gets executed, and whenever you want to print, for example, print f of the character that we have, you just do again the star s to get this character. And what you're doing here is now you're executing this pattern, which is basically printing the pattern for printing a character. You're doing this for every character in a string, and this is how you print a string. So you basically say, okay, I start at the start of the string, like here, and then for every character in sequence we just print it. So you combine a string iteration pattern plus the print pattern into a string printing pattern. I hope you can read my handwriting. Okay, does this make sense to you? Or is there anything still open? Like, if you have questions, please ask them now. This is complicated stuff, and I'm basically rushing through this just so that you can have a better start at your libft or further projects here before you get too convoluted in the beginner's mistakes, let's put it like this. So I hope this is clear. I cannot give you a list of the entirety of patterns that are out there. There's just too many of them. You have really millions of possible patterns, but there are a few common ones. For example, whenever you get a segmentation fault or some kind of crash or error, it's usually because you didn't get the conditions right. So when you have a pointer, which might be whatever pointer, so it might be a char star p, that's pointing to something. And this is invalid, so maybe null. Null is it's valid to put null into a pointer, but it's invalid to dereference this. So whenever I tell the system to get whatever is pointed to by p, again, p is just a number, or actually not a number, it's a bit pattern that tells the system where in memory it has to go and look. Most often, again, it's also the bit pattern 000. This is why it's so important to not confuse \0, null, the zero number. In the end, null is some kind of pattern defined by the system. Could be 0, could be something else. But if you put it into a pointer, and then you dereference that pointer, which basically means go to that memory location, go to memory location null, which is not existing in the system, not really, and then fetch me whatever bit pattern or character in this case. Since this is a character, it's going to give me a character out of this. When you go there, the system will just slap you again, because you're being stupid again, which could happen. Well, you forgot to check against null, because you're disallowed from accessing null. Null is basically meaning there's not a valid location here. So if you do this, it's basically the same as saying null, because p just gets inserted, and this is invalid. So the system will scream and kick you, and you're going to be sad, which is what usually happens, even to the experienced people, and you just can't find out what happened. So usually, what do you do? There's another kind of pattern, which I call the guard patterns. And these patterns you can insert between the assignment of p and the usage of p. And if you insert them here, your function will basically rectify this. So for example, it can say if p is equal to null, what we're going to do is we're going to return. Or we're going to do something else, print an error, or make p equal to something that makes sense. Maybe set p to a string, whatever, I don't know. You decide. But in the end, you check if an error condition happens, and if it does, you do something to rectify this. This is basically a guard pattern, and it looks like this. If condition that leads to a crash, then do something to rectify this. Return, or break out of a loop, or whatever. And in the end, what's going to happen with this is you insert it. Hopefully you insert the right thing in here too that matches the context. And now your system is basically protected. And in the end, if you start thinking in patterns,